In our corollary 1, we have shown that every simple zero of a multivariable polynomial over Zp obtained by reduction modulo p can be lifted to a true zero of this polynomial over Zp. Actually, it turns out that if f is a single variable polynomial, this lifting is actually unique. And in this video, we are going to prove this as a supplementary material to Sarah's book for this section, which will be used later. Suppose f is a single variable polynomial over Zp, and let a bar be a simple root of the reduction of f in Z mod Pz. Then there exists a unique lift of a bar to a in Zp, such that this a, the lift, is the root of f in Zp. A true solution. This is called Hensel's lifting lemma. The existence of the lifting is already given in the corollary 1 on page 15 of Sarah's book, which we just covered. Now it suffices to establish the uniqueness. To show this, suppose there exist two elements, a and b in Zp, such that first, they are both roots of f in Zp. And second, the reduction of a and b in Z mod Pz are the same. And thirdly, we know that at least one of them is a simple root of f modulo p. Say f prime of a is not congruent to 0 modulo p. This condition means a is a simple root modulo p. Our goal is to show that a is equal to b in Zp. Okay, how do we show this? To see this, since a is congruent to b modulo p, we can write b equal to a plus h, where h lives in p times Zp, namely p divides h. Suppose a and b are not equal, then h is not equal to 0. And again, we're going to use the Taylor expansion around a with radius h for this polynomial. By this sublemma we used in the previous video. By that Taylor expansion, we have f of a plus h equal to f of a plus f prime of a times h plus h squared times some r depending on a and h, where this r is some element in Zp. Now, since f of a and f of b are both equal to 0 in Zp, f of a plus h, which is f of b, is equal to 0, and this is also equal to 0. So we have the equation reduces to 0 equal to f prime of a times h plus h squared times r of a comma h. Now, since h is not equal to 0 and Zp is an integral domain, we can cancel h from both sides. So 0 is equal to f prime of a plus h times r of a comma h. And if you move this to the other side, we get f prime of a is equal to negative h times r of a comma h. Now, we're going to use this condition that f prime of a is not congruent to 0 modulo p. Namely, p does not divide f prime of a. What does that mean? That means we have a contradiction here. Because on one side, p does not divide f prime of a. So p does not divide left hand side. But because h, by our assumption, is a multiple of p, so p does divide the right hand side. And this leads to a contradiction. And the contradiction comes from the assumption that h is not equal to 0. So h has to be equal to 0. And therefore a is equal to b in Zp. And this finishes the proof of Hensel's lifting lemma.